Hi everybody, welcome back to Dave's Math Channel. I'm your host David Tare, and this is my continuing feature on the Math Lovers book. And last lesson, or at least last academic lesson I began chapter 6, which is on group theory. I'm now talking about group theory. And my first video on this subject was just an introduction. I said what groups are. They satisfy 4 axioms. I'm not going to go over them again. But now we're going to delve into group theory and look at some specific groups. So in particular, today we're going to look at the trivial group as well as cyclic groups, which is probably the simplest category of non-trivial groups. So anyway, let's begin. So now I'm starting a new section. This is section 6.2, which is on finite groups. The groups can be either finite or infinite, just like sets. There's finite sets and infinite sets. There's also finite groups and infinite groups. And we're going to study both of them. We'll find that they're both probably equally important. And we'll look at some interesting examples of both finite groups and infinite groups. But we're starting with finite groups. And like I said, the simplest group of all is this group called the trivial group. And it's not really a very interesting group. It's just a group with a single element. Remember I said when I was defining groups that every group has to have an identity element, which we call E? Well, the trivial group is the group where that's the only element. And you can check for yourself that all 4 axioms are satisfied by the trivial group. It's pretty easy. Maybe I should just go over them. So remember, the first is closure. Well, obviously it's closed because you can multiply E by itself and get back E. And then associativity, yeah, you can multiply E by itself 3 times. E times E squared is the same as E squared times E, which is all equal to E. It's its own inverse. E inverse is obviously E, because when you square it, you get E. E times E inverse is the same as E times E, which is E. And then finally, identity. It is the identity element by definition. So those are the 4 axioms. So you can see that the trivial group is a group. And it's not a very interesting group, but sometimes it's used. And I think we will actually see it used a little bit in this chapter. So we just have to acknowledge it's a group, and that's pretty much all we have to worry about it. But what's more interesting is groups that aren't trivial, and the simplest example of non-trivial groups are groups known as cyclic groups. And what a cyclic group is, remember I said a group is a set that has an additional structure to it. Well, so they're cyclic groups of every finite order. For instance, order 5. And usually the way we write the elements of a cyclic group, say we're doing the cyclic group of order 5, we would write the elements as a squared, a cubed, a to the 4th, and a to the 5th, which is equal to the identity. It's always true that a to the nth is equal to the identity of 5th. We're looking at a cyclic group of order n. And so that's what a cyclic group is. And then, it turns out there's also another thing that's important regarding, well, there's a couple things I'm talking about here. Maybe I should back up a little bit. If you write G as a set, so G, we usually write capital G. That's a notation we usually use to represent a group. There's what's called if you just write it as a set, the elements are E, A squared, and so on, all the way to a to the n minus 1. And then a to the n is equal to E. A more compact way to write that is with what we call algebraic notation. So we would write, when we write an algebraic notation of a group, we always put the generators on the left. We use these angular brackets instead of the curly brackets, which we use for a set. So on the left, we put the list of generators of your group. And one feature of cyclic group is they have a single generator. As a matter of fact, that's a definition of a cyclic group. A cyclic group is a group with only one generator, which we usually call A. And then now on the right, we write the algebra of the group. And this is a set of algebraic equations satisfied by the generators. In this case, there's just one algebraic equation we care about, namely a to the n is equal to e. So it just says you can take powers of a up to a to the n, but once you get to a to the n, you get the identity element back. So that's what's called the algebraic notation of G. And there's also a notation we use for writing down what a cyclic group is, and this is a little bit of a technicality here, but usually when we talk about groups, whether they're finite or infinite, we're usually interested in what's called isomorphism classes of groups. I mean, technically you might have two groups that are different groups, different sets. For instance, and maybe I should just back up a little bit here. The cyclic groups are very simple groups. Maybe I should just show some pictures. They say a picture's worth 1,000 words. So this is a picture of C7, the cyclic group of order 7. You could just think of them as numbers in a circle, kind of like a clock. Maybe it's easier to think of clocks. So the standard 12-hour clock looks like this, the hours, and this is a group. Maybe you didn't realize it, but you learned group theory when you learned to tell time when you were a kid, because the hours on a clock form a group, and usually you write 12 on top. Technically, if you're going to write this as a group, an additive group, you would put 0 rather than 12. This is addition modulo 12. So the group multiplication in this case is actually addition. And the generator would be 1. So, if you can add hours to the hours of a clock. 1 hour after 1 o'clock is 2 o'clock, 1 hour after 2 o'clock is 3 o'clock, so on. In this particular picture, they're adding 5 hours at a time. It turns out that 5 is actually another generator of C12. So you can add 5 hours to 12 o'clock. That gives you 5 o'clock. 5 hours past 5 o'clock is 10 o'clock. 5 hours past 10 o'clock, you might think that's 15 o'clock, but of course you know that you always take the remainder modulo 12 when you're adding hours. So it's really 3 o'clock. This is what's called addition modulo 12. We're actually doing modular addition here. But anyway, I'm kind of jumping the gun. I think you get the idea. So anyway, those are just a couple examples of cyclic groups. But what I was trying to say about isomorphism classes of groups, I mean, technically you might have two groups that are isomorphic. There might actually be different groups. Maybe the elements are labeled differently, or maybe one of them is a multiplicative group and one of them is an additive group. I mean, the way I've written CN here, it looks like a multiplicative group. We're taking powers of generator A. But another way you can write this is you can say it's the group generated by the number 1 modulo n, where 1 plus 1 is 2, 1 plus 2 is 3, so on. All the way up to 1 plus n minus 1 gives you 0, which is now the additive identity element of the group. And that would be isomorphic to a group where you're calling the elements powers of a squared, a cubed. I mean, I think you can kind of see. Just look at the exponents. Replace the names of the elements of your multiplicative group with the exponents. That gives you the additive group. So there are isomorphism classes of the same group. We usually think of them as the same group. So up to isomorphism, there's a unique cyclic group of order n for every positive integer n. And you can even think of the trivial group as a cyclic group of order 1. But usually people don't think of it that way. Usually when you talk about cyclic groups, you're talking about groups whose order is bigger than 1. Anyway, so that's what cyclic groups are. And that completes my video for today on the trivial group and cyclic groups. So thank you for watching. Long live math, and I'll see you guys next time.